Good afternoon, everyone. We're just going to take a couple of minutes to allow everyone to join in from the waiting room. And if you're just joining in, we're going to start in just a moment. We're just letting people join in from the waiting room. And because our event is being recorded this afternoon, and because we have a lot of videos to go through, we're going to get started. So welcome everyone to the Ontario Association of Certified Engineering Technicians and Technologists second annual Ontario Capstone Project Competition. We're so glad that you could join us this afternoon. I think you're going to be blown away by the amazing projects that you're going to see presented here today. But as we kick things off, I do ask that you join me in acknowledging that this land has been a site of human activity for thousands of years. We honor and respect the diverse Indigenous peoples connected to the territories from which each of us is joining the meeting today. We recognize the enduring presence of Indigenous peoples on this land and express our gratitude for the opportunity to live, work, and gather here. We're committed to understanding and acknowledging the histories, cultures, and contributions of Indigenous peoples, and we strive to build positive and respectful relationships. As we engage in our discussions and activities today, let us carry forward this acknowledgement and commit to working towards reconciliation, understanding, and collaboration with the Indigenous communities in Ontario, and to continuing the stewardship of the land that we all call home. I would like to start this afternoon's webinar by providing a bit of a background to today's event. One of OACETT's key mandates is to raise awareness of the contribution and competence of our certified engineering technicians and technologists. For many years, one of our strategies for doing that was through participation in National Engineering Month, or NEM. However, over time, we realized that NEM still wasn't helping us to differentiate ourselves from engineers, and we were kind of being lost in the shuffle. So when the 9 provincial organizations representing engineering and applied science technicians and technologists across the country reunited under Technology Professionals Canada, or TPC for short, in 2019, we started to talk about how we might be able to come together to enhance the collective profile of our profession, which was one of our agreed national strategic directions. In 2023, the members of TPC agreed to establish a National Engineering and Applied Science Technology, or NEAT Week, which launched in the last week of November in 2024. I'm happy to announce that this is our second annual Ontario Capstone competition, which precedes NEAT Week, as the winner from today's event will go on to compete in the national competition taking place during NEAT Week at the end of November this year. NEAT Week is intended to comprise a number of different activities involving our members, our post-secondary partners, other stakeholder organizations, and of course, the public at large. As part of our planning, we agreed that there was going to be one key anchor national event, and that was going to be a national capstone project competition. Most of the 3-year advanced diploma programs in the schools of technology across the country have culminating capstone projects, an opportunity for students, either individually or in teams, to pull together all their learning and experience over the course of their 3 years of study into one overarching project. Sometimes these projects have corporate sponsors and are designed to solve real-world problems. Others are simply the brainchild of extremely creative and talented students. Either way, I've had the privilege of seeing a number of these projects, and it is definitely an ideal way to showcase what engineering technology is all about and the future of our profession as well. However, in order to have a national competition in November, that means there needs to be a way to select the winning provincial projects that are going to compete at the national level. And that is what today is about in Ontario. Together, we are going to select the winning project that will represent our province and our association at the national competition, which will take place on Tuesday, November the 25th at 1 p.m. Eastern Time. That will also be a virtual event in much the same format, and the link to register has just been shared in the chat if you'd like to register for that event as well. Now that we have the formalities looked after, let's talk about how today's competition will work. Every college in Ontario was invited to identify projects for submission to the competition. This year, despite some of the difficulties experienced by colleges across the province, we have been very fortunate to have 6 strong submissions from 3 colleges. Each submission needed to include a brief description of the project, the full supporting technical report, the instructor's grading of the project, and most importantly, a video presentation of the project by the students. As part of today's competition, we will be showing you the video presentations for each submission for you to vote on. These videos will certainly give you a good overview of the great work that each team has undertaken. And then it's going to be up to you. In a format reminiscent of Canada's Got Talent, we're going to watch the video presentations, and then you will each be invited to vote on the project that you think should represent Ontario in the national competition on November 25th. Since you are going to be reviewing 6 projects, I highly recommend making a few notes for yourself as you go to help you remember each project and determine which one you think deserves to represent Ontario. The students have been advised that their projects will be evaluated based on the following criteria. You'll see them on the screen here: project originality, technical ability and proficiency, methodology, practicality, creativity and innovation, results and conclusions, and community leadership and importance to society. So those are the things that you should be considering when you're watching the videos. So let's get into the videos and let's take the time to introduce our first project. The projects are being presented in alphabetical order according to their project name. And when the poll comes up for voting at the end, it will be in this same order. Some of the presenters that you are going to hear do have stronger accents. So if you are having any trouble following, you're invited to enable closed captioning for the videos. You click on the CC icon that's in the bottom toolbar of the Zoom app. This is also an option if your hearing is impaired in any way, or if you have ambient noise around you. The first video that we will show today is from Conestoga College's Artificial Intelligence and Machine Learning Capstone Group. Daya Subbu, Divyamol Sunilkumar, Ismi Puluz, Shruti Nair, and Deep Kumar Patel. And I do apologize in advance if I mispronounced any of those names. This team has developed an AI-driven healthcare equity tool called CareMap. CareMap is an AI-powered healthcare equity assistant designed to improve access to care in the Kitchener-Waterloo, Cambridge area. It combines a user-friendly chatbot, semantic search, and predictive analytics to help patients easily find nearby clinics and services, while providing planners and administrators with tools to identify underserved areas and forecast future healthcare demand. That sounds quite intriguing, so let's find out more.
So our project majorly focused on the Kitchener-Waterloo Cambridge area. So here the residents face 3 common challenges like long uncertain ER waiting time, difficulty in booking appointments quickly, and limited access to the details of family doctors or kind of local providers. At the same time, the health planners often lack real-time data to identify the unreserved areas. So the care map was created to bridge this gap. It combines the intelligent data processing, conversational AI, and automation into a simple platform to make healthcare access simple, reliable, and equitable. So our purpose of care map is clear, to improve the healthcare access for everyone in this region. So our mission is to use an AI and a geospatial data to reduce the healthcare friction. And our vision is to have every resident should be able to find the timely, appropriate care. The strategies are to deliver the 3 core features: 1, the real-time dashboard, a conversational chatbot, and a AI calling agent, working together in one system. So Our first feature is a care map dashboard. The dashboard gives a patient a live snapshot of the healthcare availability. At the top, we displays average emergency wait time and average current patient times across the KWC hospitals. Below that, you will see a chart showing how many patients are waiting and how wait times are trending. What makes this differ from other datas, right? Is these datas are not static. It's grabbed directly from the official hospital website and refreshed every 10 minutes, ensuring the accuracy and trust. So the dashboards also list all the walk-in clinics and the provider details. Like for example, selecting the category dynamically relieves the provider names, opening hours, contact information, and their exact locations on an interactive maps, just like this. So for a newcomer, student, or a family under pressure, this removes the guesswork and put the reliable healthcare option in one simple view. So here we have a system to read out everything.
Average emergency wait time. Average current patients,
Just
28.
like this, everything is read out
Care
loud.
map. Smart healthcare guidance at your fingertips.
So our third feature is a AI calling agent which make the care map more than just a digital assistant. So if we launch the booking agent, the agent will be calling on behalf of the user to book an appointment. Like currently we are not integrated with system, but we have a working prototype for that. So this is our working prototype. So like here, with one tap, the agent can place a call to the clinic or the lab, request an appointment, negotiate at earliest available slot, and confirm the details, all automatical. So in our prototype demo, the agent secures a kind of um, appointment in less than a minute and confirm the details and send the information back to the patient. This is especially powerful for the people with limited internet access or digital literacy. So instead of navigating the website of the firm, the care map literally does the talking for them and making healthcare access inclusive for all. So this is the demo. Like here we can select like our purpose, location, and the date preference, like either single date or a date of range. We can do that, and kind some personal information and like the purpose of the call, looking for and maybe a family doctor. So when we submit the request here, the agent will be calling all the laboratories or the available family doctors to find out who's available. So this was a kind of call we have done in previously. So here like it gives a transcript, call summary and everything. And at the end, the appointment details will be shared to the user itself. So considering the challenges and learning, like of course, the public healthcare came with challenges. Like public healthcare data was often like fragmented, required heavy cleaning and pre-processing. Healthcare language was ambiguous and specialized, which made the query handling difficult. And we discovered the hybrid RAG pipeline was essential to balance the accuracy and coverage. And the most important is the UI simplicity directly builds user to trust, especially the users. So looking ahead, we plan to expand the care map beyond the KWC, extend coverage to the rural area where the access gaps are even greater, integrate with electronic medical records for the direct booking and secure data sharing, and more providers type like mental health, long-term care, like specialty cares. So from a business perspective, a care map offers strong ROI potential. It reduces ER strain, improve patient satisfaction, and can scale across Ontario through the partnership with healthcare system insurers, and the community organizations. So, in summary, CareMap brings together a real-time dashboard, a conversational AI chatbot, and automated calling agent into a single healthcare navigation system. Whether it's a mother seeking help at midnight, a student far from home, or a senior needing guidance, CareMap ensures like no one feels lost when they need the care at the most. Thank you.
That's some excellent work from Conestoga College, practical and helpful. For our next presentation, I would like to present a capstone project titled Digital Health Monitor, submitted by John Joseph and Kathisan Jayarantham, two students from the electronics program at Sheridan College's School of Applied Science and Engineering. Digital Health Monitor is an electronic prototype developed to measure vital signs like heart rate and blood oxygen level. The prototype also measures ambient temperature, calculates step count, and can locate the user accurately using GPS positioning. The data measured can be seen in an LCD display or can be accessed by a smartphone through Bluetooth Low Energy. The prototype can be used for research to develop applications like smartwatch and smart rings. So let's play that video to find out more.
Hello, I'm Kethishan Jayaratnam.
I'm John.
We are currently enrolled in Electronics Engineering Technology program in Sheridan College.
We'll be demonstrating our project, the Digital Health Monitor, as part of the NEET Capstone competition.
The Digital Health Monitor is an electronic prototype we designed which can measure vital signs like heart rate, blood oxygen saturation, and temperature.
In addition to the vital signs, it can also calculate your step counts and locate you accurately using GPS positioning.
The data measured can be viewed in an LCD display or read through a smartphone using BLE.
Now, let's see the prototype in working and see some of its functionalities. Our final prototype consists of two boards. The main board contains the MCU module, the GPS module with its external antenna. We have the inertial measurement unit. We have the LCD connected to it. And the second board, which contains the pulse oximetry circuitry. The two boards are connected together using flat flexible cable. The second board also has the speaker and a haptic motor connected to it for feedback. The main board can be powered using a lithium-ion battery, and we can charge it using the USB-C. Once the battery is connected, we have the device powered on, and we can see the main menu with the different options. So we can navigate these menus using these push buttons. We have the up button, down button, the enter button, and the back button. We also have a button to control the backlit display. We can turn it off and on.
But we didn't start here.
We started by making a breadboard prototype. Evaluation boards for individual sensors were tested and verified first. Then we assembled all evaluation boards with the microcontroller breakout board and verified the functionality of the system working as a single unit.
After this, we made our first prototype in PCB.
We used the ESP32 breakout directly with the PCB. All the rest of the sensors except for the GPS is populated directly to the PCB. We can use the GPS breakout also directly with the headers. We can see the PPG optical module here with the algorithm hub, and we have the IMU which is used for the step counting here. We also have the temperature sensor here which comes in contact with the skin, and we can measure the ambient temperature. So we have the switches here which can be turned on to do the specific measurement. This can be powered either through the USB by a laptop, or we can supply power through battery through these headers. So let's see it in action. We can get the values in a smartphone app. This is the NRF Connect app which is used to get the values to BLE. So when we open the app, we can see that the health monitor is right here. So we make the connection and we can see we can get the sensor readings here. So let's take the temperature measurement. So we turn the switch on, and now when we press the readings, we can see that we're getting the temperature of 28.20, which is the ambient temperature here. Now let's see some of the functionalities of our final prototype in action. We'll start with the step counting function.
So now I'm going to show you the step count. So as you can see, it's here, and once I press the enter button, as you can see, it's now 30 steps shown here. So now I'll see my step count in my smartphone as well, and as you can see, it's updated to 30 steps.
Now we'll demonstrate the GPS positioning functionality. So we are using the GPS module to get the latitude and longitude. As you can see, the blinking indicates that we have a fix. That means we have a good line of sight with the satellites, and we got the GPS coordinates. The latitude is 43.6 and the longitude is minus 79.7. If you do the reverse coordinate search, we can see that this address is Sheridan College Davis campus. Now, as you mentioned earlier, we have a speaker connected to one of our boards. So now let's see the speaker in working. Well, it might be a bit annoying sound, but we can change it to anything we want.
We also have an haptic motor which can give vibration feedback. Let's see it in action.
Our prototype still has a lot of room for improvement, especially in reducing power consumption. Also, the firmware can be changed into a real-time operating system. By adopting these changes and doing further research, our prototype can be used to develop application-specific items like smartwatches or smart rings. We hope this gives you a clear idea of our prototype's features and functionalities.
Thank you for watching our project demonstration. Hope you enjoyed it. Have a great day. Bye.
Bye.
Thank you so much to the Capstone competitions from Sheridan College. It was very interesting to see the inner workings of that prototype. Next up, we have a project titled Our Missing Middle App, submitted by Thomas McCavor, Sakin Sapkota, and Harkirat Bular of Conestoga College's Computer Application Development Program. Our Missing Middle is a web app that helps communities picture what medium density housing could look like on their own streets. Using Google Street View and AI image generation, the tool lets residents design, share, and remix housing ideas like duplexes, triplexes, and townhomes. The goal is to make conversations about zoning and density less abstract by giving people something concrete to react to. So let's play that video to find out more.
Hello, my name is Thomas McCavor, and I'm presenting on behalf of Team 8, BT, from the Computer Application Development Program at Conestoga College. Our capstone project is called Our Missing Middle, a platform designed to help communities reimagine their neighborhoods with more medium-density housing. Our mission is to encourage urban growth over gentrification and displacement by giving people the tools to visualize change in a way that feels empowering and accessible. Now, the missing middle refers to the lack of medium-density housing, like duplexes, townhomes, and low-rise apartment buildings in many low-rise neighborhoods. Our Missing Middle is a proof-of-concept web app that uses AI to help visualize what these housing options could look like in real-world settings, Toronto being our demo city. So why does this matter? Well, because housing is currently expensive and unattainable for many. When we don't have diverse housing options, it affects everyone, from young people delaying life milestones to newcomers struggling to find a place to plant new roots. Alan Watts once said, by replacing fear of the unknown with curiosity, we open ourselves up to an infinite stream of possibility. Moving on to the problem statement, we can put this succinctly. The problem we're addressing is the lack of medium density housing in low-rise neighborhoods. This isn't just a planning issue, it's a social and economic one. Expensive housing increases stress, reduces spending power, and delays major life events. It also leads to social stratification and democratic alienation. In addition, we hope this tool can empower community organizations to advocate for change using visuals generated by the app, as well as its basic social networking features. In terms of our goal, it is to create a proof of concept that municipalities could use to support zoning reform. Too often, developers present communities with plans that feel prescriptive, strangely utopian, or out of touch. We want to flip that script, give community members the power to propose ideas without needing design expertise. In the short term, we hope this sparks conversations. In the long term, we envision it supporting grassroots-driven zoning reform. And as a disclaimer, we do not envision an app like this being the solution to the housing crisis. However, tools like this that encourage out-of-the-box thinking can be helpful. In terms of getting this idea off the ground, we started by wireframing the core functionality and then built a working prototype around that vision. The design is intentionally clean and generic so it can be adapted to different municipalities. We also kept the feature set limited. We envision this app being deployed on a per municipality basis rather than one giant centralized site, such as Facebook or Pinterest. In summary, our Missing Middle is a web app that empowers users to visualize medium density housing in their own neighborhoods using AI and real-world imagery. It supports community sharing, remixing of ideas, and can integrate with local zoning data. It's a tool for engagement, education, and ultimately change. I will now move on to demoing the basic functionality of the app.
All right, so this is the web app that we have created. It starts out by showing the basic app functionality. So user has to select a parcel, choose whether to build something new or to remix a community member's previous build, and then build it up to how you would like, and then share it with your friends and community. So now that we're logged in, we can zoom in on the map here. You can see these green icons here, and these are previous builds that we have created while we were testing the app. Take a house at random up over here. So currently it's grabbing an image from Google Street View. The image you see down over here is a previous build that another user did. So here is the chat interface. We tried to make it look not like a standard ChatGPT window. We didn't want people to think that our project was just cloning an AI chat. But generally what we have found ourselves is actually cleaning up the site. And probably in a more polished end product, we would have an automatic, hey, we need to isolate the house. All right, so here we have the house just by itself. So now we can go and say, hey, let's make the house 3 stories tall. We do have our AI prompt encapsulated with using realistic building materials, not to make things that wouldn't be possible. Like you can't put a stilt hut in the middle of the neighborhood. So it did what I asked for. The building material is relatively the same. It made balconies for the 2nd and 3rd floor. And this is the general end product that we are hoping that the users would create. They're welcome to make something a lot more creative, but it also shows that change in the neighborhood doesn't have to be that jarring. And this is something you would expect to see in a mature community. In the My Community page, these are just demo organizations that we have made. The site pulls gets your geolocation and then shows you which community organizations are closest to you. So you can click these guys here and it will load the organization details and give you all their contact information. You can easily create a new one right here. Click create and it will pop up here for other users to join. So this is our most liked photo on the site so far. And then we kind of just go in descending order. We also have the standard about page here. It tells the user the basic rationale for the app here. And finally, we have a page where you can look at all the work that you've done. And if you choose to continue with the previous thing you've worked on, you can easily just go to continue and it will load that back up in the editing client here.
And that's all. Thank you for watching and check out our final product at missingmiddle.firstcell.app.
Thank you to our second team from Conestoga College. That certainly gives us another perspective about what housing could look like. And housing density and increasing housing density has certainly been one of the solutions that has been discussed for cities like Toronto. We're now halfway through our Capstone competitors. And as you can already see, this is not going to be an easy choice, especially when we have 3 more captivating Capstone videos left to view. I would now like to present a project from Adam Beck and Sam Davis from Seneca Polytechnic's Computer Engineering Technology program, titled The Screen Speeder Wireless Web Controller for the Visually Impaired. The Screen Speeder is an IoT, or Internet of Things, accessibility controller, tailored to users with visual impairments. The device aims to provide a seamless, tactile, and easy-to-use interface for navigating and interacting with web content without the need for a physical keyboard. With the use of IoT, the screen speeder connects wirelessly to any keyboard-enabled Windows device and transmits sound cues via the built-in speaker. Like a watch, the screen speeder is a wearable device that uses a nylon strap wrapped around the wrist. The controller itself sits atop the wrist and is meant to be manipulated by the opposing free hand. The underlying code and its companion dashboard app allow for reading and setting input-output values. To aid in the relay of information, the screen speeder has built-in haptic and sound feedback to provide sensory cues to the user. Let's find out more.
Hi, I'm Adam Bake.
And I'm Sam Davis.
And we're part of Seneca Polytechnic's Computer Engineering Technology program. Here today we're demonstrating the Screen Speeder, a wireless controller for the visually impaired.
The Screen Speeder is a web navigation controller for the visually impaired that leverages simple controls, fully wireless connectivity, and screen reading technology to convey information to the user without the need of screens. The controller contains various sensors and outputs to convey contextual information to the user during navigation. While the controller is connected to a host device, such as a laptop, any connected microphone may be used for speech to text, while any audio output may be used to play screen reader speech.
From the beginning of development, we had a purpose in mind: improving the online experience for those with visual impairment. Our Capstone device smooths the friction when using modern screen readers by lowering the skill level to entry. The screen speeder reduces the need for memorizing keyboard shortcuts and makes frequently used shortcuts more intuitive than standard keyboards.
This project was developed end-to-end over a 4-month period. We immediately knew we wanted to tackle the assistive technology issue. Through our research, we found a study mentioning 59% of professional workers using assistive technologies for the web found existing tools difficult to learn and use. So, we aimed to build something simple yet effective. In that same study, 96% found costs to be a major barrier for adopting assistive technologies, so we developed an economical solution for approximately $350 Canadian versus existing technologies such as Braille keyboards costing over $8,000. After countless iterations, we eventually finalized a PCB circuit that facilitated communication between sensors, outputs, and the ESP32 microcontroller.
We wanted our device to not only be simple to use, but also widely applicable and accessible. The screen speeder has only 3 requirements: a Bluetooth connection to a host, said host device uses a Windows operating system, and that on this device, NVDA screen reading software is operational. While users have the screen speeder mounted on their arm, they have more freedom of movement than a standard desk-bound keyboard.
Default mode.
After powering on and establishing Wi-Fi and Bluetooth connections, the screen speeder will be in default mode, as indicated by the green light.
USA visited link. UK link. Espanol link. Netherlands link.
Hidden mode.
In header mode, turning the scroll wheel focuses the next and previous headers when turned clockwise and counterclockwise.
Header mode.
Main landmark numbered lists heading, bulleted lists heading level, paragraphs heading level 2.
Link mode.
In link mode, the scroll wheel moves between activatable links on the current web page.
Link mode.
USA visited link, UK link, Espanol link, Italian link.
Form mode.
The scroll wheel in form mode travels between forms, such as text boxes, that receive user input.
Form mode.
No previous form field. Toolbar. Address and search bar. Edit has autocomplete control plus selected https /
Google.ca.
Google.com.
The screen speeder is fully Internet of Things capable. From this dashboard, you can interact with and monitor the screen speeder wirelessly.
Browser forward. Browser forward. Browser back.
Now, let's dive into the interior mechanisms of the screen speeder. Transitioning to a view from the bottom looking up, the movement of the internal planetary gears are much more clear.
The user spins the exterior ring, and that rotational movement is transitioned through the planetary gear into the sun gear on the shaft at the center.
Underneath this shaft is a Hall effect sensor, which monitors the changes in the magnetic field produced by a small magnet on the bottom of the shaft.
To cap off this demonstration, here is a visualization of the screen speeder's complete construction. The device contains 4 input categories. The first is the Hall effect sensor, which detects rotational movement of the navigation dial by reading field changes in the magnet connected to the dial shaft. The rotary encoder is the smaller knob, which uses quadrature encoding to cycle through 4 modes. The knob itself has a click, which sends either space or enter depending on the mode. The left-right rocker on top of the navigation dial uses push buttons to send left-right or up-down arrow key signals depending on the mode. Lastly, an internal accelerometer module detects differences between 3 axes of movements in space to send gesture signals, such as browser forward, back, and refresh.
In terms of outputs, we put emphasis on using a person's senses other than visual. Auditory feedback is delivered through an onboard speaker, relaying the various states of operation. Inside the housing, a haptic motor is mounted to the housing and can express a variety of buzzing and vibration patterns. These patterns are associated with different inputs the user makes through the screen speeder.
We thank you dearly for attending this overview of the screen speeder. Have a great day and bye for now.
Thank you to our contestants from Seneca College. It's amazing to see how students are finding new applications for AI and smart technologies, which have so many useful applications to help make navigating through life more seamless, particularly for those with physical challenges. Our next contestants are Aaron Rainford and Callan Stokuyu from Conestoga College's Mechanical Engineering Design and Analysis program. Their project, titled Subaru CTB System, analyzes the continuous variable transmission, or CVT, system inside a Subaru 3100KA770 transmission. This model of transmission can be found in a Subaru Justy, which was produced with an electronically controlled continuously variable transmission, or ECVT, from 1987 to 1994 in 2-wheel drive and 4-wheel drive options. Automobile manufacturers today are still focusing on methods to improve vehicle efficiency. This project focuses on the stress and life analysis of an early model CVT system. So let's find out how they did that.
My name is Eric Rainford. I did my engineering capstone project on a Subaru 3100KA770 CVT system. Before I dive into my project, I just want to introduce myself a little bit. I am a recent graduate of Conestoga College. I graduated their Mechanical Engineering Technology Design Analysis program. That's where this project came from. I am still a student at Conestoga College as I'm working towards getting my degree in Mechanical Systems Engineering, and I'm currently bridging into that program. So before I get into my project too, I just want to talk about what is a CVT. In case you weren't aware, CVT is a continuously variable transmission. It's essentially a power transmission system comprised of two variable pulleys and a belt. The pulleys can move in and out, changing the system's torque and speed ratios. So quick introduction of my project. It analyzes the CVT system inside of a Subaru 3100 KA770 transmission. The transmission can be found in a Subaru Justy, which was produced from 1987 to 1994. It featured a 1.2-liter engine producing 73 horsepower. History and background of the Justy itself. In 1987, it was the first vehicle in North America to feature an eCVT transmission. The E just stands for electronic. At the time, it was the first, but now many automobiles use CVT transmissions instead of automatic ones or manual ones, and it's typically due to efficiency reasons. So here's the full assembly of my CVT system. The assembly itself can be broken down into three major sub-assemblies. This is the primary pulley assembly, secondary pulley assembly, and the belt. The primary pulley assembly is comprised of a primary hub, primary pulley, and primary pulley shaft, along with bearings on either end and hardware. The secondary pulley assembly is comprised of a secondary pulley shaft, secondary pulley, secondary outer hubs A and B, a reduction gear, bearings on either end, and hardware. The belt is comprised of two steel bands made up of 10 laminated steel strips. Between these bands are steel elements. There are 280 of these elements around the belt, and they make up the body and V shape of the belt. So quick process of kind of how my project went. Essentially, I removed a CVT from a Subaru Justy. I measured and modeled all the components. I performed life and stress analysis on all components, and I tabulated my results. So here's my beloved Subaru Justy. It is a 1991 Subaru Justy, and it came with the eCVT transmission. What inspired this project is one day I was driving back from Tilsonburg, and I had transmission failure. At the time, Capstone projects were coming up, started to be talked about, and I decided, why not do my project on this and figure out why it failed? So that's what I did. Here is the Subaru Justy getting ready for its transmission to be removed. Here is the engine and transmissions themselves out of the car. And here's the transmission partially disassembled. You might notice some of the components look a little weathered. This is because from the time I pulled the transmission to the time I actually disassembled the transmission itself, it sat outside for quite some time. So on to some analysis. Some of the major components analyzed in the CVT system were the pulley shafts, the pulley and hubs, bearing life, cost, hours. So I have 232 hours into this project. That's just over a span of 7 months. This is from when I started my project to when I finished my report for the project. Conclusion. So here I quickly tabulated all my safety factors in life analysis values that I got. So I have safety factors for various diameters on the shafts themselves, along with the splines on the shafts. I also have safety factors for the reduction gear, primary pulley, secondary pulley, primary outer hubs A and B, along with some compressive stresses and other things like that. I also have my bearing life here. So one thing I should state is all my analysis was done at the worst case loading condition. This condition essentially simulates if you had your car in first gear, you revved it to its maximum power output or torque output, and you dumped the clutch. So although if you see the bottom bearing there, PB2009, 212 hours does look low. That's 212 hours at the worst case condition. So I recalculated these at a fifth gear equivalent just to show that, you know, if you're driving 80 kilometers an hour at a ratio that simulates fifth gear, you actually get over 3,000 hours of life. So 3,000 hours times 80 kilometers an hour, that's over 240,000 kilometers of life. So that bearing is deemed to be safe. I just wanted to quickly talk about that. So some additional points before I wrap up my presentation. I just want to talk about recommendations for the project. This would be increasing some of the shaft diameters that have low safety factors, along with replacing the weaker bearing out of the set of bearings. I just talked about how it is safe. However, there's no reason that I can see throughout my analysis why you'd want a weak link of a bearing there. So it should be replaced with a better suited bearing that is more on par with the other bearings in the system. Additionally, I just want to quickly talk about the relevance of my project. There's nothing new here. CVTs have been around for quite a while now, but it is important to look at older CVT systems which had flaws and failures and analyze these and see why were there flaws in the system, why did some of the CVTs fail, what are the issues, and doing so we can improve future designs. So my project takes an older design, analyzes all the flaws within it, and now knowing those flaws and having that knowledge in this report, we can better future designs of CVTs. So lastly, I just want to sum up my project. Essentially, I took something I used to use in my everyday life and I removed the transmission, fully modeled every component, measured every component, analyzed every component, and packaged all my results in a neat report. Here too, I just want to quickly show this is myself at the Conestoga College's Capstone showcase. The reason I want to show this picture is this is sort of how I would present this project to a group of people in person. So you can see I brought in a lot of my components on the left side of the table. So you can see some of my pulley shafts, some of my bearings, hardware, things like that. I also have my slideshow playing on the left-hand side, and on the right-hand side, I have an easy-to-read poster board that kind of showcases some key elements within my report. Yeah, that's everything I want to talk about today. Thank you for listening. If you need to reach out, my contact information is on the screen here. And yeah, thank you for watching. Much appreciated.
That was another interesting contribution from Conestoga College, obviously real world problem inspired and taking from the past and learning for the future. So the stakes are high. Who's going to be the big winner of this year's Ontario's Capstone competition? But before you decide, we have one final submission to show you. And this project, titled Wildfire Detection System, comes from Akash Shiji, Jessa Nehru, Christy John, Saran Soni, and Simi Johanna of Conestoga College's Virtualization and Cloud Computing program. Wildfires pose a growing threat to ecosystems, human health, and economic stability, especially in regions like British Columbia and Alberta, where dry conditions and dense forests create high-risk environments. This project introduces a cutting-edge, cloud-integrated wildfire detection and alert system powered by the Internet of Things, or IoT. By combining low-cost sensors, secure cloud infrastructure, and a responsive web interface, the system provides real-time monitoring and rapid alerts to mitigate wildfire damage. So without further ado, let's play our final video.
The critical problems that's faced are the wildfire disaster, millions of acres each year, destroying forests, homes, and lives. Current detection methods are delayed and reactive. Fires are often identified hours after ignition when they are already beyond control. This gap is what motivated us to design a faster automated solution. And the limitations of our current detection method are the existing system rely on manual patrols, watchtowers, or satellites. These have limited coverage, update every few hours, and provide impressive fire locations. In short, the current approach is too slow and unreliable to prevent major damage. Our IoT-based solution is an IoT-based automated sensor network that continuously monitors environmental conditions like temperature, humidity, gas, and flames. The data is transmitted in real time to AWS IoT Core
If a fire is detected, alerts are triggered instantly and shared through dashboards and notifications.
So I'm going to explain the rest of the slides here. So I'm going to explain the system architecture here. So the system architecture has like 5 layers. First is edge layer, which is like the EPS32 sensor, like sending data via MQTT. And then we have the injection layer, which is used for the IoT. And then we have like the processing layer, which is used for the Lambda for the analysis and the alerts. And then we have the storage layer for the DynamoDB. We are using storage and for the real time and S3 for the history and everything. And then we have the presentation layer, like React dashboard and mobile alerts are there. So this design ensures like reliability, scalability, and automation. So moving on to the IoT components. So we have used EPS32 microcontroller built-in Wi-Fi for low power operation. The sensor array like includes a DTH22 sensor for temperature and humidity. And there's also AMQP for the gas detection and IR flame sensor for fire presence also. A GPS module is also provided to get the location at the location within 2.5 meters, ensuring the responses how exactly where to act. Moving on to the Atenos code, this is a code. So what this code does is it connects the EPS32 to the AWS core and transmit like a live sensor data and triggers alerts when the thresholds are crossed. This allows like automated like real time detection without human intervention. Moving on to the AWS cloud services that we use. So we utilize like multiple AWS services, EC2 with auto scaling, DynamoDB, EFS for serverless processor, and also we use SNS for alerts, API, and Lambda, and for serverless processing and everything. And the Prometheus and Grafana, we have also used these services provide like a high and scalable availability for the closed backbone of our project. So moving on to the next slide. So the AWS cloud infrastructure. So DynamoDB like stores the sensor data with the automatic scaling. So Lambda functions are used to perform anomaly detection and even like fire probabilities analyze using like a machine learning model. So SNS like delivers instant alerts while the React dashboard visualizes the data. So the auto scaling and the load balancing guarantees like 99% of uptime. So moving on to the next slide. So that will be explained by Jimmy.
Regarding the software tools, for development and DevOps, we used React.js for the front end and Node.js with Express API for the backend, Docker and PM2 for the deployment, and Jenkins for CI/CD, and GitHub for the version control. And monitoring was done with Prometheus and Grafana. Moving on to the next slide, regarding the data flow, from the sensors will collect the data and will by using the ESP32 it will transmit the data to AWS IoT core, then to DynamoDB, then by using Lambda we'll send it to dashboard and SNS alerts. This ensures the wildfire detection and notification happen in under each 30 seconds.
From the Christie's screen, we can see that's our model, our working ESP32 microcontrollers with several sensors on it. So this is where we have, we have hosted our website into our Amazon S3 bucket. So that's the front page of our system of our website. So you can see that's when a public user can come up. So we have a home section, fire map. So fire map and report fire is one of the features we have included in day 0 release. So it's like a future enhancement which we can release in the upcoming days. So we have a login for the admin access. So the admin access is for the people who is on the government authorities and the fire department. So admin can see larger datas. Like as of now, you can see there is no active fire, and if the admin clicks on the view detailed data, they can actually see the last readings which have been gone through, like temperature, humidity, gas level, flame, all the datas, deep datas will be over here, so that the admin can see from which device it's coming from and what's the temperature and the humidity, all the level they can see from it, and the time and the date as well. So, and this is the public users can see. So when they're from the home, they can just click on the view live alerts. They can see what's going on. And there's also an email subscription where they can send, give us their email. So once they've given us their email through Amazon SNS, we can able to send alerts through email to all the public users which have been subscribed to our alerts. So now we will show you how it is working on. So now Christy will ignite a fire. So we will try to mock a fire environment. As you can see, once the Christie has given up a light, there was a fire alert status detected, fire detected on September 26 on 2:39 p.m., which exactly shows the time. So over here too, once we are done, they can see. So we indicate flame 1 as there's an active fire going on and 0 as there's no fire going on. As you can see, on those time there was a fire happened around, and now I can show you. There was a wildfire email which have been came through. So I'm now in Cambridge and that's my location. So wildfire has been detected by the sensor network, and the location and the coordinates and the Google Maps link for that one too. So that's how our product is, and that was a short demo for us. Thank you.
Thank you very much to our final contestants from Conestoga College and to all of our submissions today. I told you that you were going to be blown away. And now for the moment of truth. In just a minute, we're going to launch our voting poll. In case you need some help in deciding, I'm going to provide another reminder of the voting criteria that we would like you to consider. Project originality, technical ability and proficiency, methodology, practicality, creativity and innovation, results and conclusions, community leadership, and importance to society. Ready? Then let's launch the poll. We will give everybody a couple of minutes to place your vote. Please note that the poll is in the order of the project appearance and lists the project name and the college. Getting close to our end time, we'll give another minute if anybody hasn't had a chance to vote as yet. I think in the interest of our time, we will close the poll. I'm going to thank everybody for voting. Are we able to show the results? And so, based on that, drum roll, please. So I'm doing my very my very best drum roll on my desk. So I would like to congratulate the Screen Speeder project. I'm going to have to try to say that 3 times fast. The Screen Speeder project from Conestoga College scored as our first place project, and the project that is going to go on to represent Ontario in the national competition. The winning team shares a cash prize of $1,000 And a banner and a trophy will be presented to the college for bragging rights. This project is also going to be featured in the winter edition of the Ontario Technologist, or OT, magazine. On to our second place project. The second place project was the Subaru CTV system from Conestoga College. The second place team shares a cash prize of $700. And in third place, our congratulations go to the wildfire detection system from Conestoga College, and that team shares a cash prize of $300. I know it's a cliche to say it, but I think everyone was a winner today, with the biggest winner being the future of our profession, demonstrated by the caliber of these graduate projects. Thank you so much for your participation today and for helping us to select Ontario's entry for the National Capstone Competition. One more reminder that NEAT Week will take place the week of November 24th, and the National Capstone Competition takes place on Tuesday, November the 25th at 1 p.m. Eastern Time. So join us to help support our Ontario contestants. We will, of course, send more reminders between now and the end of November. And if you have ideas for other ways that we can celebrate NEAT Week in Ontario, please make a note in the chat or email me at cfarrow@oacett.org. We hope that you can take advantage of this event, as well as activities that will be planned with the colleges and with our local chapters. So stay tuned. Thank you again so much for joining us this afternoon, and enjoy the rest of your day.